So we were talking about big I integer and the fact that it just basically stores a little integer inside of it, a native integer type. Then we said that what they've done in the latest version of Java 7 is that they've basically supplied automatic compiler conversion so that when you say this, you actually get the line below. The compiler just converts things for you so that it's a lot less sort of dirty work on your part. And by the way, that's a trend in modern compilers and also in modern IDEs that they tend to be doing more and more and more stuff for you, which is another good reason for using them over some of the weirdities we saw yesterday with go-tos in bad places. Okay, any questions about that big I integer beastie? It's not too surprising. That integer object is more or less the same thing in its basic format. Have you dealt anything with floating point numbers so far? Python a little bit, so you had some of the discussion about floating point numbers. Well, let's start out with something really simple. What does that give for a value? Just as integers. Just zeros, right? So the remainder drops off. So this is back to grade 1 arithmetic. Think 6 divided by 7 is 0 with 6 remainder, and the remainder just gets thrown away. Okay? So suppose I make that a floating point number. What do I get if I do that? What value is going to be in that result variable? Interesting question, eh? The joy of having the IDE is that you can always just print it out or run the debugger on it. We'll just print it out in this case. Hopefully be the last line. Zero. Why is it 0? Still the same as if it were an int, right? It's still integer divided by integer on this side. So you get a result, and then that result is placed into the variable on the left-hand side. So 0 goes into a floating point number that gets converted to 0, but it's still 0. Oops. So that's a really sort of typical mistake that a lot of people will make in doing calculations with floating point numbers, is that they'll use some sort of integers in an expression. Even if you do 2.0 plus that, 2.0 f sometimes for floating point. Okay. If we do that and run it, it's still 2.0. Okay, because that thing divided by that thing is still 0 because it's still integer divided by integer. Okay, so how do you make it?
Make at least one of them a floating point.
Yeah, the trick is you can make at least one of them a floating point number, and as soon as you make one of them a floating point number, then magically it will carry the precision all across, and you're all set. The other thing that you'll see is that you can use the cast operator, so we could make that a 7, and we could use the cast, and we could say it's a float, damn it. Okay, which says, you know, take the 7 and make it a floating point number and then do the calculation. And the conversion is fine in that case. So it's always fine to convert from something from less precision to more precision. You don't lose anything going that direction. You have to be careful about using that cast operator going in the other direction where you're taking something as a float and turning it into an integer, because then you are lopping off some of the value. Okay? So that will also produce the correct result to say it's a float, damn it. Okay? That just happens to be sort of ugly, so the other way is actually probably the easier way to write it. Okay? So the rule is typically, if you want things to be a floating point number, you're probably best off, just to be sure, to always say, no, I want that part of the expression to be a floating point number. Okay? My other piece of advice for anything that involves any sort of calculation, actually two pieces of advice. The first piece is that there's a whole set of rules about operator precedence, and some people spend a lot of time in class worrying about it. The simple answer is fully bracket all of your expressions. And if you fully bracket all of your expressions, then they come out exactly the way you want them. And not only that, you don't have to read the manual to find out what the operator precedence is, and the next person who sees that code doesn't have to read the manual to find out what the operator precedence is. Okay? So you just get exactly what you want. So just bracketing everything immensely always helps. The second thing I've advised is that if that actually means something, you're almost always better off to take the intermediate values and put them into a variable and give a name that means something to the thing that you're trying to calculate, because that just makes it easier for people when they see the thing to not have to go figure out what did they mean by that. Okay? They can see immediately what you mean and whether or not you did it right. Okay, so there's a couple of pieces of advice for floating point. There are actually in Java 4 basic native types. So there's whatever a variable is. There's if I can get it right. Long b variable, there's float c variable, and there's, if I spell it correctly,
Double.
and there's double d variable. Okay? The difference between them is basically this. This integer is a 32-bit integer. That one's a 64-bit integer. That's a 32-bit floating point number, and that's a 64-bit floating point number. Typically what you see people do is they'll use the smaller of the two just because it tends to take less space. And then if they need the extra precision, they'll go for the larger of the two. The only people who really care about the difference between floats and double are people who work a lot with floating point and really care about precision. And typically we're not going to bother too much with these other than to just sort of do minimalist calculations with them. So either one will work, and you'll see me sort of use them interchangeably. The difference you can see already, one of the differences is that if we make this a double, I guess we could just use this double down here. When you initialize it here, you have to say 10, you can't just say 10.0, you have to include the F for float, whereas here you can say 10.0, I think, there we go, the equals. Okay, so if you use a float variable, quite often for the constants, it makes you put the F on just to say that's a floating point number, versus if you use the double, you don't have to say that. So either of these, for our purposes, either these two are sort of going to be interchangeable. Let's talk about the integers. If that's a 32-bit number, what's the largest positive integer that you can store in a 32-bit number? Approximately.
65,573.
No, that's a 16-bit number. A 16-bit number would be 65,536. So a 16-bit is around 65,000 plus or minus. How about a 32-bit number? Pardon me? It's not, it's more than double.
The exponent.
It's just a little over 2 billion. It's about 2.1 billion. So plus or minus 2.1 billion for that basic integer. How many people are on the globe right now?
Just over 7 billion.
Yeah, it's like it's about 7 billion, give or take a few. Okay, so the point being that if you were trying to represent how many people are on the world, or you were doing an application where you were interested in let me give you a list of countries and how many people are in each country, I think both India and China have something that's over 2 billion automatically. So if you go to represent 2 billion in an integer, you're probably going to push the limits and things aren't going to work out right for you. Okay, they'll overflow or do bad things. Okay, so it's typically important to keep at least a sense of what am I going to use this number for when you're doing an application. Okay, so up to 2 billion-ish, yeah, sure, that will work fine for you, which is probably what we're dealing with for sort of most integers numbers. That's reasonable. But if you're starting to do things that are involving over 2 billion population, I don't know, distances to stars in integer values, whatever it happens to be, volume of the sun in liters, then all of a sudden you probably need to be aware of that. What's the difference between how C and C++ do this and how Java does this? It's a really interesting question.
Well, C also has a short.
Well, there's a short version of these, and I think there's a long version of these too, maybe, if we're lucky. I can't remember. But what's the difference when you move from one computer to another different architecture in Java versus in C? There's a subtle difference. Not at all obvious.
Isn't it that the length of a long, for example, in C is defined by the specifically architecture?
Yeah, in Java, an int is always going to be 32 bits regardless of where you take it, because the virtual machine underneath ensures that you always get 32 bits for your integers, however it has to do that regardless of the architecture. C, being older and being more performance oriented, right? We'll go back to, the mid-1970s when it was all about performance. The decision when they made the C programming language was that the length of an integer should be appropriate for the native type of integer on whatever architecture you went to. Okay? Now that's really interesting because at the time, there were 16-bit architectures. Okay, so it was either 8 bits for really small numbers up to 256, or 16-bit integers for up to 32,767. And other than that, you used long, which gave you the equivalent on the old machines of a 32-bit integer. Okay, that represents a big problem. Because if you are working on a 64-bit machine in C and you do a program that calculates that says here's the population of all of the different places on the world and here's the grand total, if you do that in C on a 32-bit machine, you won't get the correct result. Yet if you move it to a 64-bit machine and compile your program for a 64-bit machine, it gives you the correct result. Oops. Okay? So that's the reason why the Java guys specifically said, since we're getting more CPUs and people are transporting stuff all over the place, we have to be really, really careful to make sure that programs work across different architectures. And so they're the same on different architectures. The real-time programmers and the embedded systems programmers are people who still tend to care about 16-bit versus 32-bit, because a lot of the architectures that they're working with are, for the things that are meant to be embedded in toasters or whatever. They want to get the cheapest product around, and they don't need to worry about counting large numbers, and so they tend to use smaller, cheaper processors in general for embedded systems. Okay? Well, one of the problems with using those smaller architectures is that if you start counting things over some length of time, for instance, the number can wrap around and it can go negative. Okay, so they basically go from being a positive number to a negative number if you add too much. Okay, I have a Sony TV, a Sony Bravia TV, which is just a little over 10 years old now. I got an update about a year after I bought my Sony TV, a little USB stick saying, please update your system by rebooting. It's actually a Linux system, an embedded Linux system. And I read the report for what they were trying to fix with the update. There was one problem where they said, if your television remains plugged in for longer than 200 odd days, all of a sudden the remote control will stop working with it. Won't be able to turn the TV on or off. Oh, well, this is sort of weird. The solution is you can either update with this USB stick, or when the problem happens, you can unplug the TV and plug it back in again, and then life will be good because that just resets everything. And so I did a calculation. I went, well, let's see, if you take 200 odd days times this many hours per day times this many minutes per day times this many seconds per day, do the calculation, what you end up doing is basically overflowing a 16-bit integer. And so someplace along the line, this programmer had written this thing that said, I'm just going to keep track of seconds for some reason. And for whatever reason, the number was used in the power on, power off for the thing. And when it overflowed, it would go negative, and then the comparison would never be true, and you couldn't actually turn your TV on or off with the on or off switch because it's controlled by the CPU. Okay? So the point of the little story is that it's still amazing. I mean, the real-time people, for instance, even 10 years ago when my TV was made, have been doing this for 30 years. And guess what? Somebody got it wrong. They used the wrong size of thing, and they weren't all that concerned about it. Okay? So it does make a difference, and it is something that you have to be careful about. But for the typical stuff that we're doing, where we're counting in hundreds and thousands and 10,000s, number of students at Camosun, number of people in Victoria, we don't typically see a problem. Okay, but be careful about it. Okay, so we've worried about making sure our precision is right, and so we've done the cast to do that. We've seen the four different native types, and I said the other day that some programming languages are now not bothering with the native types. They're just making everything an object, so they'd use big I integer and big D double, and they would let the compiler worry about how do I get the best performance out of something when you're doing a calculation. Okay. Again, just so that you get sort of more abilities in the thing, and it makes the code all look the same because everything becomes an object. And Java's still got this split between the native types versus objects. Okay. Well, let's try something else then. Suppose we print out the value of (10 divided by 3.0). What are you going to get for a value? What do you expect? 3.33333333, on and on and on.
Ad infinitum.
Well, unfortunately, there's a limit to what can be expressed with that type of number. Let's just see what we get.
5.
5? Yeah, it ends in a 5. 4, I was sort of expecting, 3, hopefully. 4 seems a little weird, but 5 just seems like totally out to lunch. Okay, so there's another important thing about floating point numbers. They lose some precision at the end, particularly for things that repeat, and if the 10 has been converted from an integer to a floating point number, then it's got those last few digits that are sort of suspect. The 3.0 is sort of suspect when it's converted to a binary, a base 2 sort of system, and the result of the thing is just not what you'd expect. Okay, it's just a little off. Okay, may or may not make a difference to you, but something to be careful about. Okay, well, let's try this then. Let's go right to the maximum. And I've got two things that are the maximum precision that I can use. The only difference between those two doubles is that I've moved the decimal point. So it's still, that one has the 6's after the decimal point. This one has the 6's before the decimal point, but the magnitude of the division is the same for both of them. Produce the same results or not?
No.
You would expect them to, because we're just sliding the decimal point around. Well, let's just do it this way. So you get somebody who writes something like this in their code. Is it going to print that or not?
Nope.
You would, looking at this code, you would sort of expect it, would say the doubles are the same. We'll just print them out. Oh, it didn't print out anything. Well, let's just see what the values are here. There's the two numbers, and they're, gosh golly, almost the same, except for that very last digit. Okay? So the point of this exercise is that comparing floating point numbers with double equals to see if they're the same, always a bad thing. Pretty much 99% of the time it's a bad thing. You're never going to get the result that you expect. So what should you do?
Take the difference and round to a certain number of decimals.
Yeah, you really only care sort of plus or minus within some number of decimal points whether or not they're the same thing. Okay, so the moral of the story here is that floating point numbers should always be compared by some plus or minus value, probably. Well, let's just do that for the pure fun of it. So here's public Boolean within magnitude, or I don't know, whatever you want to call it, within some delta value. So I'll have double first, double second, and what the heck, double, I'll call it plus minus, just because I can't think of the correct terminology. Okay, so normally you would expect that they would be the same, and if for some reason first minus second is less than plus minus, oops, making a mess. Return false. Oops. is that right?
Greater.
First minus plus minus. I'll get it right yet. I think I need these on the other side. See how bad my math is? Give that a try. And do the same thing for, probably the plus one makes more sense. So we'll do that one first. People think of positive things better. Plus minus is that much greater than the second. Does that make sense? So if I take the first and add the delta and I go past what the second is, then I'm out of range. And if I take first minus something and it's less than the other one, okay, well, let's just try that. Okay. By the way, notice how if you have a question about that, what's the best thing to do about whether or not that code is correct?
Write a J-unit test.
Write a unit test. And you can do, here's two values, here's one that's less than this one by this much, here's one that's greater than this much. You can do the combinations to see. Okay, so there's your exercise if you want, write a unit test. But basically you're going to have to play that sort of game of saying, are they within some tolerance? I guess the word here is probably tolerance. By the way, tolerance is treated in two separate ways. I always think of tolerance as being plus or minus this one. Sometimes the mathematicians think of it as just the positive difference, so the absolute value, right, of the difference between them, which is not quite the same thing, I don't think. Okay, so there is, in unit tests, there is assert equals, where you can give it one double and another value that's the positive difference between the two, and it will say whether or not it's out of range, except that the positive difference always confuses me, so you can tell that I'm not a math guy. Anyway, the point being, you're probably going to have to write some little routine like this. Interestingly enough, every year when I have this discussion, I go and I check and I see, is there some library routine someplace that will do this for me instead of me having to write it all the time? And every year I can't find it if there is one. Okay, I know unit tests have one, but typically you want one in your actual code also, and I can't find one. The capital F float and doubles don't have them. I can't find the equivalent of like a capital C collections library that, you know, a capital N number library that deals with these things. I just don't see one. That could be I don't read a lot of the mathy type code, so I always end up stealing one and making one. Okay, something along that line. It's not like it's too difficult to write. Okay, by the way, it's also possible if you want to write things in scientific notation. So that also works. Okay, so that's 1 with 6 zeros before it, or something like that. Okay, so you can go back and use all of your scientific notation capabilities. That works just fine for both floating point and double numbers. Okay, so the mathematicians like to use that. What if we print that thing out? We get basically the same number. So somehow it was smart enough to go, oh, okay, if you use scientific notation for declaring it, I'm going to use scientific notation for printing it out for you. Isn't that nice? Don't know how it did that, but it somehow magically knows. Okay. What if I want that number printed out so that I can actually see the decimal points on it? Oh. Well, here's one way of doing it. this thing called a decimal format class. And the decimal format class, you just specify a pattern of what you want the thing to look like, basically. And in that case, when we print it out,
how does the formatting code do it?
well, we'll just have a look and see what we get with this thing, formatter dot precision. Okay, so it just does basically what it tells you for the format. So if you add another 0 in there and then print it out, it just plops the 0 on the end. So you basically can say, here's what I want the number to look like, the number of fields I want it to fill, and it does the correct thing. Now you can go, this is a case where if you want to see all of the things that you can do with decimal format, it's not a bad idea to go and look in the documentation, and it's probably easier to read it here. So let's just go find decimal format. Almost got it. And here's the decimal format stuff, and oh look, there's patterns and fractions, and this is one where there's too much documentation at the front, because they proceed to tell you all sorts of wonderful things that you can do, all the sorts of options that are available in order to do it. They're nice enough to provide some sort of sample code, and oh, it looks like you can even get it localized decimal format to specific countries. So it will use whatever locale you happen to be in and do the appropriate things. So, you know, the British have this thing about commas. The Europeans, I guess, have this thing about commas rather than decimal points and numbers. So it will just automatically print it out based on where it is. Okay, so there's some advantage to doing this over rolling your own and just saying, I think it's always going to be this, right? So internationalization means that you have to take extra effort. And so there's, you know, summaries of all of the methods and all of that sort of stuff. You can also actually, the parse thing is used to translate a thing back into a number, so it's going the other direction. So there's stuff to do that. So there's just a billion examples of things that you can do in there with numbers. Okay, so number format, but you know, typically you can get by with just doing the simple thing if somebody actually ever gives you a sample piece of documentation. There, it's easier to just go see that and use that, and in most cases, for whatever you're trying to do, that format will probably work for you. Okay, so there's the decimal format guy. Let's do a couple more here. Let's try an example of bigger versus smaller. So there's our first double value, whatever it was, and the second double value, which is the bigger one. Okay. What do we have that we would use to try to figure bigger or smaller for anything? What have we been doing?
Compare to?
We've been using compare to. So if we were to write a compare to for these things, if they were integers, we would just take the difference like I've done here. What's the problem with taking the difference between those two numbers?
It's not accurate. If you convert it to an integer, it will truncate them.
Well, yeah, I mean, if you convert it to an integer, it'll truncate them, right? And they only differ by the last very few digits of the thing. Even if they were just two normal floating point numbers, they would still be, one would be bigger and one would be smaller. So the problem with taking the difference between these things is the result that you get is also a floating point number, which, you know, even if it's 0 isn't the mark here, you know, and plus or minus 1 aren't going to work for us. So we're in a bit of a quandary in how we do this, right? We can't just use the difference like we could with integers. Well, there's a couple of ways that you could do it, but really it turns out that that this may not be a surprise. Our friend big D double instead of small d double actually has a compare to inside of it. Okay? And so you actually don't have to know how to compare two floating point numbers yourself. If you really want to know, you can drop them into a big D double, and since big D double is now an object, it has a compare to that will do the correct thing for you. How does it do its job? It actually has to have an if statement to say, well, okay, which, you know, if the difference is, you know, less than 0, then this one is larger, and I'll return a 1 or a minus 1. Otherwise, if the difference is greater than 0, I'll return a plus 1. So it's not that difficult to do, but it's done with an if statement. You do the subtraction and then an if. It's not just a direct subtraction. And the only result, it's interesting because I've been saying that with numbers, we always want the magnitude of the difference, right? So with integers, you get the difference between our weights. The magnitude is important. With floating point numbers, when you use compare to, you don't get the magnitude of the difference. You just get plus or minus 1. So it's the exception to the rule because it can't give you the proper magnitude of the difference back. Okay, so there's the exception to the rule. And that gets us through, one other thing for being able to print out values. There's a fairly recent addition to the Java libraries, and I always think of this one as being specifically for C programmers. Okay, so there is a system.out.format, if I get it right, where what you do is you specify, let me just do one, 4.2f, my first double. I think that'll work. I'll just put some stars beside it so we can see it. Hope I did it right. No, a backslash and, sorry. There we go. Okay, so the explanation of this is that the original sort of way of formatting things coming from C was to use something that's not called format, it's actually called printf. And if you go look in your C documentation, the way that printf worked for floating point number or for any number is that what you did is you made a string, what they called a formatting string, and the string contained both the text you were interested in printing out and some special symbol that said here's where to insert the number in that stream of text. So you can put stuff after the text too. And all that happens with those is that it goes along and it searches this string for every percent sign it sees. It just takes the next variable that's listed here and prints it out. So if we wanted to do another one, it would be first double, comma, second double, like that. And then it won't print out unless you put in the percent sign in there to specifically say, I want to see that value. So the usual mistake that C programmers made is that they'd put 2 or 3 or 4 variables at the end of the line that they wanted listed out, but there wouldn't be a matching percent sign for each one of them to make sure it actually did get printed out. They'd either add 1 too many or 1 too few. That's the sort of common error and Java tends to catch that. And so you can specify this is the total number of digits, and this is the number of digits, I think, after the decimal point, if I remember right. So that gives you, with 4, you get 2 before and 2 after the decimal point. Okay. This thing, I say it was added to appease C programmers, because C programmers were a lot more used to doing that than doing the pattern thing. And so they just stuck that in with system out format, and it basically follows the C convention. Okay, and even though I'm an old C programmer, I tend to like to see the pattern version a little bit better, because this one has too many uncaught errors, not so much in Java, but more in C itself, from too many or too few things on the line just not getting done properly. Okay, so tomorrow what we'll do is we'll start on files, finally. So we'll talk about various things we can do with files, probably for 3 or 4 days. And with that, we're done.